Stevens, Steady State Exercising. This report will be based on the findings of a test of what happens to bodily functions, such as the energy system and respiratory system when undergoing steady state exercise. Steady state exercise is exercise in which the intensity remains at the same level throughout, and therefore the heart rate remains constant while doing the exercise. This is according to Prezi.com, which says steady state exercise is activity that achieves a balance between the energy required by working muscles and the rate of oxygen and delivery for aerobic ATP production. An example of steady state exercise would be a run where you run at the same intensity for the whole duration of the run. A null hypothesis is the common view of what the score will be / the average scores. A one-tailed hypothesis is when you argue the score will be in one direction, for example if it's higher than the null. And a two-tailed hypothesis is when you argue that the score will be in either direction, for example it will be higher or lower than the null. My hypothesis for what would happen to the cardiovascular system is that the heart rate will increase slightly during exercise and then plateau, and systolic blood pressure will increase slightly, and diastolic will decrease slightly before both then plateauing. For the respiratory system, my hypothesis was that the breathing rate will increase slightly during exercise and then plateau, and for the energy systems, that the main energy system that will be used during steady state exercise will be the aerobic energy system. Blood lactate levels won't increase during exercise as the participant will be working aerobically, and oxygen saturation will increase rapidly and then plateau. Our method was that before exercise, we will take the weight of the participant and then find 2% of this weight. This 2% will then be added to the weight of the bike to add resistance when doing the exercise, otherwise it would be too easy for the participant. We will also take the height of the participants so we can find a comfortable seat height during the cycling. We will take measurements for heart rate, blood pressure, breathing rate, blood lactate levels, and oxygen saturation before exercise, so we can compare the results of these things before, during, and after steady state exercise to see if any changes occur. The final thing before undergoing exercise will be for the participant to undergo a warm-up. This warm-up will be a light cycle for 3 minutes with no added weight on the bike. The reason for the warm-up being a cycle is because this will then warm up the appropriate muscles for the exercise. When the exercise starts, the participant will cycle for 20 minutes, where we do a series of tests on him to make sure he is doing this exercise in his aerobic zone, and to see the changes that happen during steady state exercise. Fred will take the heart rate of the participant every minute by noting down the reading on the screen due to the heart rate monitor being in use. Fred will also take the readings for the Borg scale every 5 minutes by asking the participant how hard he thinks he's working. The blood pressure will be taken every 2 minutes by Ellis by getting a reading from the blood pressure monitor. The breathing rate will be taken every 2 minutes by Ashley by counting the amount of inhalations in a 30-second period and then multiplying this by 2. Along with this, Ashley will also take the oxygen saturation every minute by taking down the reading on the finger clip. And finally, the blood lactate levels will be taken at the start of exercise, at 10 minutes into the exercise, and at the end of exercise by Ash, and all these results will be taken down by Sam, who will also oversee keeping the time. All these readings will then be taken again after exercise at post 1 minute and at post 2 minutes, so we can compare all the results for before, during, and after exercise to see if any changes take place and why they take place. Stroke volume is the volume of blood pushed out of the heart, specifically the left ventricle per beat. The average stroke volume for an adult is 70 millilitres per beat, whereas the average for an elite athlete is around 100 millilitres per beat, and this allows for the heart rate of the athlete to decrease so they can work harder during exercise. Cardiac output is the amount of blood pumped out of the heart per minute, measured in litres per minute. The average cardiac output for an adult is 5 litres per minute. When exercising, this can increase to around 20 litres per minute, or for an athlete to around 35 litres per minute. Blood pressure is the pressure of the blood pushing against the arterial walls in the circulatory system. Breathing rate is the number of breaths taken per minute. The average breathing rate for an adult is between 12 and 20 breaths per minute. However, for an athlete, this can decrease to around 6 to 8 breaths. The vascular shunt is the distribution of blood around the body. This changes during exercise to get more blood to key areas of the body for the body to continue exercising at the level of intensity. Vasoconstriction is the constriction of blood vessels which causes the increase of blood pressure, and vasodilation is the dilation of blood vessels which causes the lowering of blood pressure. The explanation of my hypothesis was that For heart rate, during steady state exercise, the heart rate will increase during the anticipatory rise and slightly more during the beginning phase of exercise. This is because of the proprioceptors, chemoreceptors, and thermoreceptors all detect the change in the state of the body and cause there to be an increased release of adrenaline from the adrenal glands, which stimulates the SA node, which in turn activates the contractions of the heart to happen more often. However, the heart rate will eventually stagger and then plateau. This is because the demands of the working muscles are being met at the heart rate, so it doesn't need to increase any further. After exercise, it gradually decreases. During an extended period of time performing steady state exercise, particularly in a hot climate, a steady state heart rate will gradually increase. Stroke volume also increases during the anticipatory rise and then further during the beginning phase of exercise until it reaches a point where no more blood needs to be pumped out of the heart per beat to reach the demands of the working muscles. This increase happens because the SA node is stimulated by the increased release of adrenaline from the adrenal glands, which then stimulates the heart to beat faster, and so there is more blood entering the heart. This is venous return, which is the rate in which blood returns to the heart. Therefore, the heart must pump out more blood per beat to empty the heart, and so stroke volume increases. Because of the stroke volume increasing to a point where the amount of blood is meeting the amount of the body needs, it staggers and plateaus. After exercising, it gradually decreases. One of the reasons stroke volume increases states that stroke volume increases in response to increase in blood volume filling the heart. Cardiac output increases due to the increase in both stroke volume and heart rate, as there is more blood being pumped out of the heart per beat. Stroke volume and there being more beats a minute heart rate means there is an increase in blood being pumped out of the heart per minute. During steady state exercise, the cardiac output will also stagger and plateau due to the stroke volume and heart rate also plateauing. After exercise, when both stroke volume and heart rate gradually decrease, cardiac output slowly decreases. Cardiac output increases proportionally with exercise intensity, which is predictable from understanding the response of heart rate and stroke volume to activity. For blood pressure, during steady state exercise, systolic blood pressure increases slightly because the amount of blood going out of the heart per minute per beat increases. Therefore, the amount of blood pushing against the arterial walls increases, and diastolic pressure decreases or stays the same due to the vasodilation of the blood vessels. They both then plateau as no more blood is coming out of the heart, and there is no further vasodilation. After exercise, they both go back to their resting values, as the amount of blood leaving the heart decreases, and so the amount of blood pushing against the arterial walls decreases, and so the pressure decreases and vasodilation decreases. Exercise raises systolic pressure, but there is only a slight change in diastolic pressure. Immediately after exercise, there is a fall in systolic pressure, as the skeletal muscular pump is no longer pumping blood from the muscles to the heart. The blood flow changes during steady state exercise to allow more oxygen and energy to reach the muscle groups that are working during exercise. The cardiovascular system takes on vasoconstriction and vasodilation to make these changes happen. The amount of blood that travels to organs that are seen as not being vital by the body receive less blood, such as the kidneys and digestive tract, while the lungs, myocardium, and skeletal muscles receive more. Blood flow is controlled by pressure. This is achieved by pressure by the vasoconstriction and vasodilation. For thermoregulation throughout steady state exercise, plasma volume increases. This increase supports sweat gland functions for the body during heat stress. The body tries to maintain the correct volume of plasma in the body for the demand of the exercise in which the body is undergoing. During exercise, several powerful physiological mechanisms of heat loss are activated to prevent an excessive rise in body core temperature. Venous return. During steady state exercise, there is an increased venous return as the stroke volume increases, and so more blood will be returning to the heart, which is when the deoxygenated blood returns to the heart. Deoxygenated blood returns to the heart slower during exercise due to low pressure. The muscles help support the increased blood flow by squeezing the veins around the body. During exercise, the rhythmic pump of your muscles facilitates venous return by forcing blood through the one-way valves that lead to the heart. This law suggests that stroke volume can increase due to two different things occurring. One of these is the increase in venous return happening, as if there is an increase in blood returning to the heart, then the stroke volume must increase to empty the heart of all the blood. The other one is because it can also increase due to there being a greater contraction of the cardiac muscles while undergoing exercise. The observation that stroke volume and hence cardiac output increases with increasing preload is known as Starling's law of the heart. It is defined as the relationship between stroke volume or cardiac output and end diastolic volume or venous pressure. Energy system. The main energy system that will be used during steady state exercise will be the aerobic energy system. The reason for this is because the initial energy system will be ATP, which will last for the first 3 seconds. Then it will go to ATP PC, which will last for another 5 to 10 seconds. And after this, the body will start to use the aerobic energy system as there is oxygen present when breaking down the glucose. This can last for around 4 to 10 minutes. Aerobic glycolysis has a slow rate of ATP production and is predominantly utilised during longer duration, lower intensity activities after the phosphagen and anaerobic systems have fatigued. Breathing rate. During steady state exercise, the breathing rate will increase during the anticipatory rise due to there being an increase in adrenaline in the body, which is released from the adrenal glands, which causes there to be an increase in carbon dioxide concentration and a decrease in oxygen concentration to the blood. This stimulates the respiratory control center to increase breathing rate so the body can exhale the carbon dioxide in the body, and also to inhale more oxygen so that there is more oxygen in the blood to get to the working muscles. During exercise, this increases more due to a higher amount of carbon dioxide and lower amount of oxygen as more oxygen is being used, and so more carbon dioxide is being created. Around the midpoint of exercise, the breathing rate will stagger and plateau because the amount of oxygen needed in the body and the amount of carbon dioxide in the body is being sustained at a good level for the body to be able to carry on working, so the breathing rate doesn't need to increase. Decreased blood oxygen, the amount of oxygen in blood, and decreased blood carbon dioxide concentration stimulates the respiratory center to increase breathing rate. Tidal volume is the total volume of air that is inhaled or expired during a singular breath. The average tidal volume at rest is around 500 milliliters. However, during exercise, this can double to around 1,000 milliliters. The reason this increase happens is because there is an increased demand for oxygen in the body at the working muscles for them to continue working at the same intensity of exercise. Therefore, the tidal volume has to increase so that the lungs can draw in more oxygen per breath to reach these demands, as only the increase in breathing rate wouldn't meet the demands of the body. The apneustic center sends signals for inspiration for long and deep breaths. It controls the intensity of breathing and is inhibited by the stretch receptors of the pulmonary muscles at maximum depth of inspiration, or by signals from the pneumothoracic center. It increases tidal volume. From the blood pressure results graph, the results show that the diastolic blood pressure starts high and decreases rapidly and plateaus around the 50 to 70 mark, while systolic blood pressure starts around 100 and increases around the 14-minute mark, and then decreases after the exercise has been completed. However, because we only have one set of data with more than 2 results taken down, the results may be inaccurate, and so we'd have to redo these tests to see if they are accurate. Oxygen saturation. For oxygen saturation, all the results started around the 80 to 90 mark, with Rachel getting an outstanding score of 99. The oxygen saturation then increases to 95 to 100 and plateaus around the 8-minute mark, 99 for Billy and 97 for Luke. However, again, Rachel's score is the outstanding score as it decreases at the beginning to 66 and then increases at the 11th minute and plateaus at around 98 at the 12-minute mark. This plateau then finishes with a decrease at the 20th minute mark and during the post-exercise period. A heart rate. From the graph, we can see that both Billy and Luke start around the same heart rate, Billy with 95 and Luke with 90. However, Rachel's heart rate is significantly higher than both of these at 128. All three of these people then have an increase in heart rate, with Billy reaching around 160, Luke reaching 122, and Rachel reaching 159. However, from here, all three have different things occur. Rachel's heart rate drops down to 101 until the 7th minute, before then returning to 190 and plateauing around this until the end of exercise. Luke's heart rate gradually increases until around the 12th minute mark of exercise, where it plateaus and stays around the 160 mark. And Billy's heart rate spikes up and down throughout exercise. For example, it goes from 198 in the 12th minute to 115 in the 14th minute. Lactate results. Before exercise started, the 3 people undergoing the test all had very different levels. Billy had a score of 1.2, Luke of 9.3 and Rachel of 15.1. However, Billy rose to the highest score of 22.1 during exercise, while the other 2 decreased to around the score of 6. After these changes in score, they all plateau at these respective scores. Luke and Rachel both then had a small period of plateau at this time before having a slight increase just before the end of exercise, whereas Billy had a slight decrease before the end of exercise.